note that this webinar is being recorded. If you have any objections, you may disconnect at this time. If you need closed captioning, please go to captiontext.com. The confirmation number is 2857016. And please mute all your lines if you dialed into the presentation today. Today we are delighted to welcome our presenters, Dr. Niall Bolger from Columbia University and Dr. Jean-Philippe Laurenceau from the University of Delaware, who will be joined by our very own Dr. Erin Hennessy, who will moderate the session. A very brief word about logistics, and we will be off. The session is being recorded, and we've muted all lines to help us avoid any background noise. For those who have dialed in by phone, please mute your phone. We encourage questions. They can be submitted by using the chat feature on the right-hand side of your screen. Type your question into the chat field and submit it to me, the host, Tracy Goldner. Feel free to submit your question at any time, but we will be opening the session for questions when the presentation is finished. Without further ado, it is my pleasure to turn the meeting over to Dr. Erin Hennessy.
Thank you, Tracy. It is my pleasure to discuss the FLASHE study with all of you today. I also want to make one additional point. Sometimes if you have your phones on speaker, in addition to mute, it can cause background noise. So if you could just take yourself off of speaker and mute yourselves, it will help us in the recording, because this video webinar will be archived on our website for future reference. So we really want to make sure that the audio comes across clean and clear. So I'm here just to give you a few facts about FLASHE as quick as possible, because I don't want to distract from the main point of our talk today. But we thought it might be helpful to let you know that FLASHE is a one-time cross-sectional survey. It is from a U.S. panel. It's a consumer panel. It is balanced to be representative of the U.S. demographic population, but it is not nationally representative, but it's similar in those characteristics. It was conducted via web, and we had two modules, one that was focused on diet and one that was focused on physical activity. And those modules were completed by parents and their adolescent child between the ages of 12 to 17 years. And the data was collected between April and October of 2014. The study was conducted by the National Cancer Institute through the Division of Cancer Control and Population Sciences Behavioral Research Program, and it was implemented by WestStat. So if you haven't had a chance to yet, I encourage you to go to the FLASHE website via this web address. So we will have the information about this webinar and about all of our FLASHE materials from this portal, and you can go and you can visit and view our conceptual model, which I'll show you in a second, our flow diagram. You'll be able to access the data when it's available to you, and the dyadic resources page. Right now, what we've made available to you are all of the survey instruments and questions, along with the code book and our methods report of how the study was conducted. So you can learn a lot about FLASHE and start generating your research questions. But the data will become available to you focused on diet and the demographic modules later this month in February. We will be doing a rolling data release, so the physical activity survey data will be coming sometime later this year. So as I mentioned, we have the FLASHE conceptual model. Our primary outcomes were focused on diet and physical activity behaviors, but we also have other cancer-preventive health behaviors such as sun safety, sleep, and tobacco. Because this webinar is focused on dyadic, we're going to tell you a lot about the richness of the fact that it's a dyadic study design, so that parents and children completed some survey items that were assessed in the exact same way. That doesn't mean all of your FLASHE analyses have to be dyadic. You can absolutely do an individual level analysis, but there is a lot more richness that you can get from the FLASHE study design. We have focused factors on the adolescent psychosocial variables, parents, the home environment, and the community neighborhood environment. The FLASHE flow chart, so we had a sample starting of just over 5,000. We had just shy of 40% who completed enrollment, and we had 2 study arms, those who received the survey only and those who were allocated into what we call our motion study group. So a subsample of adolescents were asked to wear a wrist-worn accelerometer for 7 days, and that group also received the surveys in addition to wearing the accelerometer. All of that information makes up our analytical database, and I want to point out that we have just shy of 1,500 dyads who completed all 4 surveys and returned the monitor if they were supposed to do so. But if you were to do an individual analysis or focus your analysis on a different type of question, your sample size might fluctuate and get a little bit higher than that. Without further ado, I would like to turn this over to Dr. Niall Bolger. Thank you, Niall.
Thank you, Erin. So what you see in front of you now is an outline of what we're going to talk about. So first of all, we're going to cover what are dyadic data, what are we doing when we do a dyadic study. We're going to talk about the FLASHE variables that are dyadic. We're going to talk about a central focus of the analyses we're going to show, which is to explain dyadic covariation in FLASHE variables. So we're going to talk about what that covariation is, how you measure it, and my colleague Jean-Philippe will be taking you through a model that will help to explain the covariation, and that's called the actor-partner interdependence model. We'll be occasionally referring to various sources, and we'll have a list of those at the end. And then we will look at all the questions that you've sent us, and we'll try to answer as many as we can. So what is a dyadic design? A dyadic design is one where the investigator samples pairs of people from a population. And in addition, each person in the dyad provides information on the same variables, and that's going to be very important. The results of analyses of dyads will allow you to draw a conclusion about a population of dyads. And although, as Dr. Hennessy pointed out, you can treat this data set as samples of individuals, it is important to think of the phenomenon as a population process of dyads, and this is something that our statistical tests will be, that's the inference to which our statistical tests will be directed. There are 2 types of dyads normally talked about. One is indistinguishable dyads, and these are dyads such as gay and lesbian couples, friendship pairs, identical twins, where we have no reason to distinguish between the members. I mean, we keep them separate in our analyses, but we don't focus on characteristics of the members per se. The other major type is distinguishable dyads. These are heterosexual couples, parents and children, an older and younger sibling. So of course the FLASHE data set that we are working with has distinguishable dyads because we have parents, it could be a male parent or a female parent, and we've teenagers, which can be male or female. And we have roughly equal numbers of all 4 groups. Now today we're just going to be talking about the overall sample. So what are dyadic variables that are assessed in FLASHE? Well, we have dyads of one parent and one teen, and they provided lots of information on health-relevant variables. The two that we're going to focus on for our analyses are parent and teen reports of fruit and vegetable consumption and each of their senses of self-efficacy for fruit and vegetable consumption. And we're going to think of the efficacy variables as potential causes of the fruit and vegetable consumption, and we'll get to that in a minute. But first, there's some issues in dyadic data analysis that we should draw to your attention. The most obvious one is that the observations from parents and teens in each dyad are likely to be non-independent, and that breaks a golden rule that we are used to following when we work with ordinary survey data. So you might be asking the question, is there a problem if we were to use regression or ANOVA or any kind of general linear model to analyze dyadic data? And the answer is yes, there is a problem. And so we will be talking about an approach that circumvents that. But we should also draw your attention to the fact that it is usually precisely because the dyad members are dependent or are not independently sampled, that is actually the process that we're interested in, because we're interested in health-related variables that are usually very similar or could in theory be similar between the dyad members and certainly with parents and teens. And a proper dyadic data analysis then will allow us to understand how much and why this may be the case. Okay, now what processes could lead to covariation between dyad members? Well, we distinguish two kinds, but there are others. But one kind is common influences that are due to the fact that parents and teens share the same local culture, the same local geography, the same local economy. And these can lead parents and teens, for obvious reasons, to be more similar on health-related variables such as diet. Then the prime focus of our analyses are within dyad causal influences. So dyad members can affect one another's thoughts, feelings, and behaviors, and it's that process that we're particularly interested in. So for example, parents and teens can have similar diets because parents often buy and cook family meals. So let's get to some research questions. So first of all, do parents and teens actually covary in their fruit and vegetable consumption? We'll start there. We'll also ask if the independent variables that are of interest to us, the efficacy variables from parents and teen, if they influence both the teen and the parent's consumption of fruit and vegetables. So we're thinking of having two independent variables, efficacy of the teen and efficacy of the parents. And finally, we're going to, in a quantitative way, talk about how much these intradyadic processes can explain why the parent and teen are similar. So the goal is that we're going to try and explain the similarity. Now, how can you measure this similarity or covariation in dyadic data? We will use a Pearson correlation denoted R. Most of you are probably familiar with the Pearson correlation. It's an index of linear covariation that ranges from -1 to 1. So if R is positive, then when one dyad member scores high, the other tends to as well. If R is close to 0, then knowing the score of one dyad member tells you nothing about the score of the other. And we don't expect that to be the case. Nor do we expect the correlation to be negative, although it can possibly be. And that would be a case where one dyad member scores high, and that would imply that the other dyad member scores low. So we want you to have a clear understanding of the measures that we're going to use in our analyses. So what you see in front of you now are the questions that we used to come up with an index of fruit and vegetable consumption. So both parents and teens were asked the following question: during the past 7 days, how many times did you eat? And then there were questions about fruit, like apples and bananas and melons, green salads, non-fried potatoes, and non-fried vegetables. And for each of these, the response options were none, 1 to 3 times per week, 4 to 6 times per week, once per day, twice per day, 3 times per day. So we took these 4 variables and we created an index by summing the scores and rescaling the results such that 0 was the lowest possible score on these items, and 10 represented the highest possible score on these items. So the theoretical range of the scale goes from 0 to 10. Now, what about our independent variable, efficacy for fruit and vegetable consumption? So the question there was a single item: I feel confident in my ability to eat fruits and vegetables every day. And the response was from strongly disagree to strongly agree. We again created a version of this efficacy variable such that 0 was the lowest possible score and 10 was the highest possible score. Now finally we get to the data. For our analyses, we're working with 1,486 dyads. This N is a little bit different from the N on the screen earlier that Dr. Hennessy was talking about, because the underlying data set is periodically updated. So we have actually a few dyads more than are in the official, the most recent version of the data set. So given that we have these dyads, now let's look at the distributions of these variables. So what you're seeing in front of you now is a scatter plot matrix, and we're looking at the upper left-hand columns, and we'll start with the first of the 4 variables, efficacy of the parent, and we can see that the distribution of this variable is well, it's called negatively skewed, but most of the scores tend to be up the high end. The mean is 7.6, the standard deviation is 3.0. So that's what the parents look like as a group on this variable. Now, if we go down to the next diagonal element, we see the equivalent for the teens. And it's quite clear that there are many similarities. The means are basically exactly the same. The standard deviation is slightly smaller for the parents. Now, what about the dyadic covariation in these variables? Well, you can see I'm using my cursor, and I hope you can see the cursor, to highlight a scatter plot. And I should tell you that the data in this scatter plot have been jittered slightly. Now, jittering means that we've added a slight bit of noise to each score so that when we plot the data, individual observations are easier to see. And this is a common method in statistics these days. The correlation is small, 0.21, but it's still something that is going to matter, as you'll see when we get to doing the modeling. Now, let's look at the dependent measures, they're going to be the fruit and vegetable consumption of the parents and teens. Here again, we see similarities. Now we have, for the parent fruit and vegetable consumption, we see this positively skewed variable such that the mean is down the low end, 3.2 on a 0 to 10 scale, and with a standard deviation of 1.6. And then for the teen, the mean is 3.0 and the standard deviation is 1.7, but very similar shapes. The correlation, however, in this case is much larger, and the scatter plot that you see here is almost a classic bivariate normal distribution. So this is going to be the focus of our investigations, this substantial dyadic covariance. And now I'm going to turn over to Jean-Philippe Laurenceau, my colleague, and he'll take you through the modeling part.
Okay, thanks very much, Niall. So now we're going to move to discussing one, at least, explanatory model for this, this dyadic correlation, dyadic covariance in food and vegetable consumption that we see between the teen and the parents. This model is called the actor-partner interdependence model, promulgated probably most by David Kenny, social psychologist. And just to remind you, this is the dyadic covariance or correlation that we're trying to explain here, this correlation of 0.49 between the fruit and vegetable consumption of the teen and fruit and vegetable consumption of the parent. So here's a depiction of the actor-partner independence model, the APIM. It's a path diagram. So those of you that might be familiar with path diagramming from a SEM framework, this should seem somewhat familiar. We're going to talk a little bit later about how to estimate the various paths and other quantities, other parameters that are in this model. The other thing that's worth noting before we start launching into some of the aspects of this model is that we've dramatically simplified the details and the assumptions underlying this model for the purposes of this brief webinar. So, for example, there are going to be likely a lot of other influences that would need to be taken into account to really understand the dyadic covariance between parents and teens and their fruit and vegetable consumption beyond efficacy. But we're just going to be focusing on efficacy for now. So you can see we have actor effects, we have partner effects. What makes a model like this a little different than the typical ordinary least squares regression is that we have two outcomes in this model instead of just one. And so the efficacy predictors, their role and their influence is on both of these outcomes simultaneously. We'll start by focusing on the teen efficacy as a causal influence, if you will, of both the teen's own fruit and vegetable consumption as well as the parent's fruit and vegetable consumption. So we'll take a little bit of time and break this down. So when a person's score on a predictor variable has an influence on that same person's score, that's an actor effect. And when a person's score on a predictor has an influence on his or her partner score, that's called a partner effect. And so the teen has an actor effect, it's depicted up here, and a partner effect is depicted over here. We have corollary actor and partner effects also for the parent, depicted in this red path, and also partner effect for the parent, depicted in this red path. Those of you that might be familiar with path modeling would see that the equations that underlie the actor-partner interdependence model really are basically a system of equations, in this case a pair of equations whose parameters are simultaneously estimated. So down here in the blue box, we'll see that we have a teen equation, a regression equation, and we also have a parent fruit and vegetable regression equation. The in the teen regression equation, we have the teen actor effect, which is the regression of the teen outcome on the teen efficacy scores. And then we also have the parent-partner effect, P sub parent. So that's the regression of the teen's outcome on the parent's efficacy scores. So the actor effect A, that would refer to this path, to this coefficient here. The parent-partner effect would refer to this coefficient here. And then we have residuals for the teen outcome that represent unexplained variability in teen fruit and vegetable consumption. And then we have a second equation, the fruit and vegetable consumption for the parent. And so the parent also has, or the parents have an actor effect depicted by this path down here. And then there is a teen partner effect, which is the effect of the teen's efficacy on the parent. And that would be depicted here with this diagonal arrow. And we have a residual also for the parent. So the key thing is that all of these paths are being estimated simultaneously. And as a result, we can also estimate what's called a residual covariance, which is this curvy-headed arrow out here on the right. It indicates how much of the basically unexplained variance in fruit and vegetable consumption for the parent and teen remains after accounting for both teen efficacy and parent efficacy. So that initial 0.49, that's what we're going to want to explain, and we should expect that the remaining or the residual correlation should be lower if our predictors are doing a good job of explaining the covariance. So just a couple words now on estimating the parameters in the actor-partner interdependence model. Basically, there are kind of two classes of software that can be used. One is comes from the SEM tradition, so any of the programs that are used for doing path modeling or structural equation modeling can be used, so M+, LISROL, AMOS, SAS-Proc, Calis, and for our users, there are multiple packages. One that we have seen some use in is Lavon, which is very similar to M+. We'll be showing our results with the M+ program and its associated output. We'll also, but at the same time, you can also use a multi-level modeling approach or tradition represented by packages like SAS-Proc Mixed, HLM, SPSS Mixed, and then for our users, the LME4 package. So we should note that for the same data and for the same model, as long as you specify things correctly in both of these traditions, you'll get exactly the same results out to a few decimal places at least. So that's somewhat reassuring. And to help facilitate your use of dyadic modeling with these data, we have provided in a user's guide that was mentioned earlier the script and the code for the analysis that we're depicting here, that we're about to go through in some detail, and then also for other related dyadic analyses, as well as visualization, which we think is very important to be able to visualize the data while you're engaging in the analysis process. So to remind you, this is the dyadic covariance that we're trying to explain using our model. And here are the standardized coefficients, essentially, from M+ that we get for representing all the parameters in this model. So because they're standardized, all these effects are in standard deviation units. Of course, the estimation is done simultaneously for both the teen and the parent equations and their associated parameters. The model, of course, allows for residual correlation that we see here. And then I'll also point out that before going into interpreting some of these coefficients, point out that there's an R² for each of the outcomes. So there's an R² of 20% for the fruit and vegetable consumption for the teen, R² of 13% for the fruit and vegetable consumption of the parent. But what we're really interested in, besides just explaining variance in each of the outcomes, is explaining the covariance between these outcomes. And that's exactly what the actor-partner interdependence model will allow us to do. So there are 4 groups of effects that you can focus on in the actor-partner interdependence model. The first set we call the teen effect-driven aspect of the APIM. So essentially, it's the effect of the teen's efficacy on both their own fruit and vegetable consumption as well as the fruit and vegetable consumption of the parent. So so this 0.41 coefficient indicates that teens who differ from each other by 1 standard deviation on efficacy, because that's the focal predictor, but whose parents are the same on efficacy, because we're also controlling for the parent efficacy here when looking at this 0.41. So these 2 teens who differ 1 standard deviation on efficacy are predicted to differ by 0.41 standard deviation units on fruit and vegetable consumption for the teen. Okay. The teen's actor effect has the following interpretation. So teens who differ from each other by 1 standard deviation on efficacy, the teen's partner effect, excuse me, teens who differ from each other by 1 standard deviation on efficacy, but whose parents are the same on efficacy, okay, are predicted to differ by 0.13 units on parent fruit and vegetable consumption. So these teen-driven effects here can be viewed essentially as a common cause of both the fruit and vegetable consumption of the teen and of the parent, and as a result will explain some portion of the dyadic covariation between the teen and parent fruit and vegetable consumption. So basically the teen-driven effect is calculated as a product of these 2 paths, the 0.41 and the 0.13, and that's what we're depicting down here in the red box. And this represents a piece of the dyadic correlation that we are trying to explain. So there's a teen effect-driven piece, and then we also have a corollary parent effect-driven portion. Again, here's the actor effect, but this time for the parent. 0.31 has the same interpretation essentially as we did for the actor effect for the teen. And we have also the parent's partner effect. And if we take the product of those 2, remember these are in standardized units, so these are beta weights, if you will, we get a piece of the dyadic covariance that's explained by this parent-driven effect. Again, parent's efficacy in this case being a common cause of both the fruit and vegetable consumption of the teen and the parent. So now we move to the third kind of effect in the APIM model. It's the actor-driven effect. So here we're focusing on the actor effects, as you can see here in the red. But now we are going to start really with this initial correlation between the parent and teen efficacy scores of 0.21. Although it's small, it is large enough to be able to actually carry through their respective actor effects, this covariation here, to create some degree of dyadic covariation in the fruit and vegetable consumption scores of the teen and the parent. So these actor effects, even though they're labeled actor, they also create dyadic covariation because they start off with the covariation of the efficacy scores and basically carry that effect through to the teen and parent dyadic covariation. So there's an actor-driven effect, which is also a dyadic effect, and it represents a unique piece of the covariation. And the way that you get that is you multiply the corresponding effects in the boxes. So the actor effect for the teen, which is the 0.41, times the actor effect times the dyadic correlation between the efficacy scores, 0.21, and then finally by the 0.31, which is the parent actor effect. And finally, we get to the partner-driven effects. So similar interpretation, except now we're focusing on how the initial dyadic covariation between the efficacy scores carries through the partner effects for both the teen and the parent. And again, we multiply 0.13 times 0.21 times 0.11, and we get a proportion or a piece of the dyadic correlation that is partner effect driven. So if you've been following along, you'll see that we have essentially decomposed the dyadic correlation of teen and parent fruit and vegetable consumption into four pieces, four effects, if you will, that derive from the actor-partner interdependence model. There's the teen-driven effect, and we saw the calculation of that before, but by the product of the teen actor effect and teen partner effect, and that represents 11% of the initial covariation. So the initial correlation is 0.49, 0.488 rounded. So 11% of that initial correlation is teen-driven, represented by teen-driven effects. We have 7% for parent-driven effects, 5% for actor-driven effects, and 1% for partner-driven effect. We add all these pieces up, it turns out that approximately 24% of the fruit and vegetable dyadic correlation, which is that 0.49 that we started off with, is explained by the actor-partner interdependence model effects. That leaves 76% of that correlation that remains to be explained for the total of 100%. So I'll note that this is a little bit different perhaps than focusing on just the R-squared of the fruit and vegetable consumption for the teen and the R-squared for the fruit and vegetable consumption of the parent. We're actually looking at the underlying dyadic covariation and trying to get a sense of why there's such a strong correlation between the fruit and vegetable consumptions of the teen and parents in this sample. And we see that, the lion's share seems to be captured by teen-driven effects in this APIM involving efficacy. So we're getting toward the end of our webinar. We'd like to take a moment to acknowledge the influences of at least a couple, if not more, folks in the field. So these ideas that we talked about here are not really our own. They come from prior work from folks like Kenny Cashy and Cook, and they're the authors of a seminal book on dyadic data analysis by the same name in 2006. And as well as Richard Gonzalez and Dale Griffin, who are the authors of several classic papers in the area of dyadic data analysis and wanting to treat dyads with respect statistically. So we give references to these in this next slide here, the Kenny Cashy Cook book in Guilford Press, and then Gonzalez and Griffin papers. We also provide the Cohen, Aiken, and West, which is the paper that describes how to take the units of a scale and then be able to convert it from a 0 to 10 scale that we talked about earlier. And for those of you that might be interested or wondering, well, how would I extend this to a longitudinal context if I had dyadic data that were repeatedly assessed over time? Well, we provide some references here. One Guilford book that we recently published, but there are some a chapter and also a paper about this issue of longitudinal data in a dyadic context. And now I'll turn it over to Dr. Hennessy for the question and answer portion of the webinar.
Thank you both very much for your wonderful presentation. As Dr. Laurenceau just mentioned, we are going to turn it over to you for questions. And just to move forward, you can submit your questions in the chat feature that's on the upper right-hand dialog box. And all you have to do is just type it in and hit submit. And so we've had a couple of questions. I got a couple of questions via email. And one of the questions was how you know whether these are statistically significant, the relationships that you were just talking about.
Oh, sure. Well, so it turns out that all the paths that were in that APIM model, the final APIM model, all those paths were statistically significant. We didn't emphasize significance primarily because with a sample size of 1,480 some odd couples, even tiny correlations will turn out to be significant, but all of those are statistically significant at the 0.05 level, and that's indicated also in the M+ output that goes along with this example.
Okay, and you know, if a teen's partner effect is not statistically significant, does it mean that the teens do not influence their parents for the outcome of interest?
Well, if I can jump in here. No, I don't think you could draw that conclusion. First of all, because there are many things that could affect the outcome of interest, and we are just showing you efficacy. And also, although in this case it's not a problem, but if you have smaller sample sizes, you know, focusing just on the significance can be misleading. It is important. These path decomposition methods that we've been using, they work, and they'll only work if you use the actual coefficients in the model. So you would leave all the coefficients in the model. Yes, if some are non-significant, then I wouldn't trim that model. And indeed, instead of significance, I would focus more on the confidence interval for that effect, because you can have non-significant effects, but their confidence intervals, so the values that are consistent with the data that you have, they can include values that are large enough that you would not want to ignore them. So you can have a non-significant effect, but it can still be consistent with a much larger effect. You just don't know.
Great, that's helpful. And I know you touched upon this in the webinar, but I just kind of want to go back to revisit sort of the point of, you know, how is this really different? Like, why can't I just run separate regression models? What added value am I getting by really kind of doing it in an actor-partner interdependence model?
Sure, so if I can just step back perhaps to an earlier slide here. Well, these effects, maybe it's easier to see it on with the path model. These four types of effects that we talked about, really the only way that we could actually get those is if we have dyadic data and we estimate a model where both the teen and the parent's outcomes are simultaneously part of the model. So that's really the only way that we could actually get all of these effects, because all of these effects here are dyadic effects. They're just driven by different parts of the APIM model. So if you were to do a regression model with just the teen outcome, teen fruit and vegetable outcome, let's say, you'd get the R squared, right, in terms of, you know, the variance explained in the teen outcome, and you'd get a kind of teen actor effect, but and you'd get a partner effect, but you wouldn't actually be able to get, technically speaking, the right actor effect, because, again, I'll point it out here, if you use the teen actor effect, if we focus on the teen's outcome, we regress fruit and vegetable consumption of the teen on the teen efficacy. We get the actor effect, but we also need to do this regression as well, simultaneously, right? And so this is going to give us the parent partner effect. So we'll get the teen actor effect, but the parent partner effect. But if we want to also get the parent, if we want to also get the corresponding ones, we're going to need to also include the parent's outcome. But then, most importantly, it's this covariation that we're trying to explain. If we don't have both of these outcomes in the same model, we can't explain this covariation, or at least we can't do it in an efficient way. So, so it's suboptimal. It may not be incorrect necessarily to focus on each of the partner's outcomes, but it's suboptimal in terms of making the most out of the dyadic data that you've collected.
Great, and another question came in sort of stemming from this line of thought, but what benefit does this APIM approach have kind of over another method such as a repeated measures model?
It's a good question, and essentially if you run what I now consider the modern version of repeated measures analyses, which are the mixed level or multi-level modeling tradition, you will get the same results. And in the user's guide that will be available to go along with this webinar, we show how to do the analyses both ways. So using the equivalent of a repeated measures analysis and using a structural equation modeling analysis, and you get the same results. I think depending on what you're familiar with or what you're used to, you might find it easier to work with the SEM tradition. Dr. Laurenceau, I think, is rooted in that tradition more than I am, and I'm rooted more in the multi-level modeling tradition than he is. So we've been able to establish, and others have too, that structural equation modeling and multi-level modeling in certain cases are the same. They're just different ways of partitioning variance.
Okay. Could you sort of compare and contrast what the differences would be if you were just using the teen data to control for the parent data? So if you were just looking at one outcome and you were using some teen variables to control, what would you lose insight-wise?
Well, again, I think it comes back to this covariance here. I think it comes back to this initial, where we're starting here. If you want to understand why is it that when a teen eats more fruit and vegetables, his or her parent also tends to eat more fruits and vegetables. If you want to try to understand why these things go together, then you need to have a model that estimates both outcomes simultaneously. And so, again, it wouldn't be incorrect to, for example, if you're focusing on the teen outcome but you control for the parents, let's say, you put in efficacy of the parent as well as looking at efficacy of the teen. And I'm not sure if the person that's asking the question is saying, well, what if you controlled for the fruit and vegetable consumption of the parent? Well, that would kind of be a different question, but it still wouldn't get at this idea of, okay, how much of this relationship are we explaining, this covariation here, this correlation between the fruit and vegetable consumption of the teen and the parent. So it really is it's just a different thing, basically.
Yeah, it's a different kind of research question. Great, and so with the number of tests that you've done, do you have to be concerned about sort of the multiple contrast and kind of controlling for that issue of the multiple comparisons?
I don't think so for a model like this, because everything that we've drawn your attention to are fundamental parameters of the actor-partner interdependence model. And these are things that we ought to have expectations about and plans to look at ahead of time. So I don't think in this case I would worry about multiple comparisons. Obviously, if you have a very complex model with lots and lots of independent variables and perhaps mediating variables and dependent variables, well, then you might be in the situation where, yes, you've looked at a lot. Perhaps you've looked at 100 of these coefficients. Well, statistical theory tells us that 5 of those will be significant just by chance. So that definitely is a case where you should be worried about multiple comparisons. I wouldn't be worried about it in this particular example, or an example that has perhaps maybe 1 or 2 more independent variables.
Great, thank you. And I think we got a question that came in around a topic that we've internally talked a lot about, and that's the issue of moderation and whether parent-teen sex is a moderator. And can you deal with that? How could you deal with that? So if you were to think that the relationship between parent and teen fruit and vegetable consumption differs as to whether it's a mother-daughter pair or a mother-son pair, and can you handle that in this kind of model, and you know, sort of just any recommendations you have about that?
Sure. Yeah, well, that was actually something that crossed our minds when we were working with this data set. That is, you know, do some of these effects that we see here, you know, in the APIM that we've talked about, do they differ or are they different depending on what kind of pairing of parent and child, and in this case, or parent and teen. So in a sense, we have a 2-by-2 crossing of male and female parents, male and female teens, and so we have these 4 different kinds of dyads, and we can see whether or not these effects differ. And that is very possible. I mean, it kind of just, the reason we didn't do that is just for the sake of time. However, it's exactly that kind of analysis that we show how to do. So it would be, you know, a moderation analysis within the context of this APIM in the user's guide that we provide, or that will be provided on the FLASHE website for the dyadic component.
Great, okay. Yeah, and in the interest of time, we weren't able to show some of that sample code, but in the next couple of weeks, we will be posting that sample code, and it's, you know, been designed and had a lot of internal review so that hopefully on your end, it's a little bit more plug and play so that you can run the scripts and get the output and, you know, kind of learn in addition to reviewing this webinar and some of the other materials we'll have on there. So hopefully that will be helpful to you as well. We had a couple of questions too, and I think this comes up a lot in terms of, you know, having the same variable for both members of the dyad, and are the metrics kind of equivalent? And so there was a question around why you were converting the response scale for the fruit and vegetable outcome from, you know, the 1 to 5 to a 1 to 10. Is that something that's standard for dyadic analysis, or is that something that's specific to this particular data set or something else?
That's a good question. And, well, we could have left the variables on their original scales, and both parents and teens got essentially the same questions. The efficacy was on a 1 to 6 point scale. The fruit and vegetable consumption was on a 1 to 5 point scale. If you look at standardized results, the actual scaling doesn't matter. But I think we've been influenced by this paper by Cohen, Aiken, and West, and we've given the site for it, where when we standardize things, we're subtracting the mean and we're dividing by the standard deviation. Now, that's an ideal thing to do when you have normally distributed data, but if you don't, I think it's interesting to just create a dimension on which the 0 means the lowest and 10 means the highest. It doesn't have to be 0 to 10. It could be 0 to 1. It could be 0 to 100, or any other interval. But this is an alternative to standardizing the variables, perhaps before you start on the analysis. As it turns out, it really doesn't matter whether you look at the data standardized or unstandardized. The tests of significance are exactly the same. So it's really a matter of choice what you do. And you notice that when we were doing the path decomposition, we used the standardized results. But I think there will be occasions where you're dealing with variables that, are things like blood pressure. And, these are things that have meanings in their original scale. You may not want to standardize those. And so you will be working with the unstandardized estimates. You'll see in this user's guide that we keep talking about that, we show you results, the N+ results in both forms. And I think what's most important is to see whether the verbal description of the effect of the kind that JP used earlier, talking about what the 0.41, for example, of the actor effect actually means. If the verbal account is more clear and it communicates better, then that's the one you should use. The tests of significance are always the same.
Okay, so it sounds like it's a little bit of a combination of it. Could be a characteristic of both the dyadic analysis and the nature of your data in which you have it.
Yes.
Okay, that was really...
But it's not required for dyadic data analysis.
Yeah, okay,
so, yeah.
Great. That's very helpful. Will we, in the interest of time, because we only have a minute left, there's a couple of questions that we weren't able to get to, but I will do my best to respond to you in a timely fashion. We had a couple of questions around sort of the purpose and, what was the nature behind FLASHE. And I would say one of the biggest things was understanding cancer-preventive health behaviors from a conceptually multi-level approach, in addition to this dyadic design, because when we did a scan of the literature, there were really no public use data sets out there that would allow you to assess these different behaviors from that and from a parent and child perspective. So that was one of the main drivers, was to be able to fill that gap and to provide you as researchers the data that you needed to answer unique research questions that would help us in the realm of cancer control and cancer prevention. So if you have any other questions, please feel free to email us at nciflashe@mail.nih.gov. We want to continue the discussion online, and you can go to our website. That is where we'll have an archive of today's session, which will be available. You will receive an email with a link from us to the website when these materials become live. So we will notify you. You don't have to keep checking back. Thank you all so much for your time, and thank you again to Dr. Bolger and Laurenceau. Have a great day. You can sign off now.